Continuing with the previous example, we're trying to find the area underneath the curve y equals x squared plus 2 between x equals 1 and x equals 3. Now what we've done so far is we split this region into 4 vertical strips, and we estimated the areas using upper and lower sums. Using 4 rectangles, we found out that the exact area under the curve was somewhere between 10.75 and 14.75. Now let's see if we can improve the estimate a little bit by using 5 rectangles instead of 4. So first of all, let's see if we can figure out what the width of each rectangle is going to be. Notice that the total width of this interval from 1 to 3 is 2 units. So if I divide that into 5 equal pieces, each piece is going to have a width of 2/5. In other words, 0.4. So if I start at this left end point and add 0.4, I'll get to 1.4, adding again, 1.8, again, 2.2, and then 2.6, and then 3. And those are going to be the endpoints I'll use to cut this into 5 strips of equal width. So when I divide into rectangles, R1 through R5, each rectangle has width 0.4. So if we use this if we use these tables for the lower sum and upper sum, we can go ahead and fill the base in for every single rectangle. Now, let's take care of the lower sums first. For the lower sums, I want to use inscribed rectangles. So that means that the rectangles fit under the curve. And since this function is increasing, that means that on any little interval, the left endpoint is lower than the right. So if I want the lower sum, I have to plug in the left endpoint. If my function had been decreasing, then it would have been reversed. So here, if I want the height of R1 for the inscribed rectangle for the lower sum, I'm going to substitute 1 into the function f. So the height of rectangle 1 for a lower sum is f of 1, which is 3. The base is 0.4, so the area is 1.2. Over here, on the other hand, if I wanted to find the height of the first rectangle using a circumscribed rectangle, the circumscribed rectangles are on the outside like this. So for the first circumscribed rectangle, the height of the rectangle is given by the right endpoint, since the right endpoint is higher than the left. And I get the right endpoint, the height of the right endpoint, by substituting 1.4 into this function. So for the circumscribed rectangle, the height of rectangle 1 is f of 1.4. And if you substitute 1.4 into x squared plus 2, you should get about 3.96, actually exactly 3.96. And the area will be 3.96 times 0.4, so 1.584. At this point, I recommend that you pause the video and fill out the rest of both tables. I can't pause the video without starting a new one, so I'm just going to start filling it in. For rectangle 2, the height's given by f of 1.4, which is 3.96. When you multiply by 0.4, you get the area of 1.584. Continuing, the height of R3 is f of 1.8, which is 5.24. Multiplying by 0.4, you get 2.096 is the area. The height of R4 is f of 2.2, which is 6.84, giving us an area of 2.736. And the height of R5 is f of 2.6, which is 8.78, giving us an area of 3.504. Adding together those 5 numbers, we get 11.12 as our lower sum. So we know that the true area is bigger than 11.12. Switching to the circumscribed rectangles, you probably noticed that the first 4 rectangles here had the same area as the last 4 rectangles here. So after the 1.584, you should have gotten areas of 2.096, 2.736, and 3.504. But we need to do a fresh calculation to get the area of R5. The height of R5 is the y-coordinate of this point, which I can get by plugging 3 into the function. And f of 3 is 9, and 9 times 0.4 is 3.6. Oops, sorry. 9 plus 2 is 11. And 11 times 0.4 is 4.4. So the upper sum is going to be the sum of the areas of these 5 circumscribed rectangles, which is 14.32. So now, if we can see that if we use 5 rectangles instead of 4, then the total area is going to be somewhere between 11.12 and 14.32. So for 5 rectangles, we get a better estimate of between 11.12 and 14.32. You can see that this new interval is narrower than the old one. So if we wanted to continue improving this, we could choose more and more rectangles. Instead of using 5, use 10 or use 100. Since the tables get really large, I guess one option would be to use Excel, and hopefully you'll find some pattern. Or we can do some algebra so that we can do it a little bit easier, so we can find out a bunch of possibilities at once. The goal, though, is that as the number of rectangles gets bigger and bigger, hopefully this interval is going to get narrower and narrower. The lower sums are going to get bigger, and the upper sums are going to get smaller. And just as if we were using the squeeze theorem, the true area should be squeezed between those 2 limits.